This conference will now be recorded.
Okay, let's get started. For those of you who haven't been at the previous webinars that I did the past 2 weeks, my name's Doug Maddox, and I've been working on the development team for eQuest and DOE23 for the past few years, and have also done quite a bit of testing of the tools. And today we'll be talking about the new variable refrigerant flow capabilities. The previous 2 webinars, which are topics 1 and 2 and 3, are now posted on my website. They have both the PDFs of the slides and on YouTube there's videos, recordings of these sessions. So I plan to do the same thing for the VRF. So today, variable refrigerant flow, and start out with some basic concepts about how the systems are configured, and then basic model inputs that are required for the new model. Talk about sizing, and then just some additional background that might be useful if you want to go deeper into your inputs. And then finally, talk about the interface for variable refrigerant flow in eQuest. So variable refrigerant flow is it's a refrigeration system that basically serves air handling coils out in a building, and it can simultaneously have if you have a heat recovery is the term model. You can simultaneously have some units in cooling mode, which are shown on the left, and other units in a heating mode. And all of those are served by a single compressor unit or series of compressor units. And the new model in DOE23 and eQuest is a component-based model. So each of the components that are drawn in circles here are actually modeled separately in the calculations, and also there's separate sets of inputs for each of these. The condensing unit, the inputs are combined into one component. So it's a component that includes the compressor and the outdoor fan. But in the simulation itself, they're treated as 2 different components in the model. So that kind of gives a general idea what the scope is. So this component-based model is a little different from the way simulation engines have handled VRF in the past. In the old methods and the performance curves that you'll find published out in the field generally are usually given as a function of an average indoor wet bulb temperature and outdoor dry bulb temperature. And that kind of waters down the results a little bit, or the calculation process a little bit. So it's somewhat limited in the accuracy and in the range of things that you can actually model if you use that approach. Also, the performance curves are generally based on data that's developed for design purposes and not operating purposes. So there's some limitations in the data because of that. In the new DOE23 method, the impact of each indoor coil is evaluated separately in the calculations. And it uses this detailed heat exchanger model that accounts for indoor humidity and temperature in the hourly calculation. So it's a fairly accurate and more detailed model than what was done in the past. Also, the compressor performance curves are given in terms of the actual refrigerant temperatures rather than as an overall system curve that is based on temperatures of the air. And so that's a different approach. In general, you could kind of think of the new DOE23 3.3 method is kind of an analogous to a chiller model, where you have a network of indoor coils that are either drawing or rejecting heat to a refrigerant loop, and then an outdoor unit, which would be kind of equivalent to the chiller, that handles the net heat rejection of the loop. And the state of the refrigerant loop then is controlled at a fixed point or with reset controls, depending on selections you make in the inputs. So one issue with this approach is that performance curves are not yet readily available to differentiate one manufacturer from another. The default curves that come with the program are, I think, reasonable and give, fair analysis of a typical VRF system. But if you're trying to compare one manufacturer to another, that doesn't necessarily give you the ability to do that because the manufacturers don't have that data yet. You can compare one efficiency level of equipment to another, and I'll get into how you do that in a little bit. One other thing to point out is that this methodology of a component-based model is consistent with the latest Energy Plus physics-based, they call it their physics-based VRF model. And we actually studied that model quite a bit as we were developing because we wanted to have our performance curves be compatible with Energy Plus. So people who use both programs or people who are developing for one program can use the same curves for the other. So I've tested that, and I'll show you in a little while the comparison between the curves of the two programs. So when you're first getting into the model, you need to know what requirements as far as the minimum input parameters that you need to input to represent a VRF model. And then, so I've got those kind of the basic required things listed, and then some additional things that I recommend including. So the required, I'll go ahead and read through those items. You basically have to create a condensing unit, and you have to assign it a type, and it's either a VRF heat pump, which means it is either serving units in cooling or in heating, but it doesn't actually allow the simultaneous heating and cooling of the system. Or you can have what the industry calls VRF heat recovery type of system, and that one does allow simultaneous heating and cooling and basically recovering of energy from hot zones to cool zones, and it becomes a more efficient operation. You also have to specify the locations of refrigerant pipes, and I'll describe what these terms header and branch mean in terms of the program in a little bit. At the system level, you have to only apply a VRF to either a package variable, a PVVT system in DOE2 or a DOAS system type. So it's only applicable to those two system types. So you have to know that and limit yourself to those system types. And then you specify, in order to set up a VRF in a specific system, the heat source to be equal to condensing unit, and then the system condensing unit keyword is set to the username of the condensing unit that you want to assign to that system. And for people who are eQuest users and aren't so familiar with the DOE2 keyword language, I'll be talking in terms of DOE2 keyword language for the first part of the seminar, and then at the end, I'll give a cross-reference between these keyword names and the names that are used in eQuest, and show you, I'll give you a quick rundown of where to find things in the eQuest interface. Okay, so then there's these additional recommended entries into the program, and I'm going to talk about these in the next few slides. So I won't read through each one. So the first is calculation of the electric input ratio for model input. So there's a few things that you have to be aware of and careful about as you collect data from manufacturers' literature. First, that you want to locate AHRI-rated values of EER in the literature. And as I've been working with these systems, I've found that some manufacturer literature will have values that are listed at conditions other than AHRI. They'll often have both available if you look hard enough, but what you find first might not be what you're looking for. So you have to make sure that it's specified as being rated at AHRI. And also, their AHRI will specify conditions as either non-ducted or ducted. And even though you may be looking at the rating values for the outdoor unit, which doesn't actually ever connect itself to a duct, the AHRI specifies that those would be tested with either ducted or non-ducted indoor units. So when you're getting an EER for use in a model, you want to make sure that the value you're getting is for a non-ducted test. So that's something to pay attention to. Next, that AHRI values, again, even though they're being listed for the outdoor unit, the power consumption in the EER includes some assumed value of indoor fan power. So you have to do a calculation to remove the indoor fan power in order to calculate an EIR from the model. So none of this is an exact science because of the way things are, the data is published, but you can, I think, get reasonably close with the approaches that I've described here. So since we're using the value for non-ducted indoor terminals, then my suggestion is to assume a value of indoor fan power of 0.1 watts per CFM, which I believe is typical of non-ducted indoor units. And then the next few lines here show how you would calculate the indoor fan electric input ratio and then subtract that from the EER in order to get the outdoor unit EIR. So the next item then you need to pay attention to is the fan power of the indoor unit. And this is handled in a kind of a simplistic way, but probably a reasonable way in DOE2 by defining for each indoor unit a terminal type or VRF term type. And that terminal type will trigger some default value for the watt per CFM. So for example, if I choose a terminal type to be a surface, that's the surface mounted type, which is basically ducted, and the default value is 0.125, which is a little bit higher than what I showed in the previous slide of 0.1. But that's the way that the default's set up in the program. And again, I think that's a reasonable value. If you have a ducted terminal type, the ducts have significant static pressure that are associated with them, and that will increase your fan power to the default of 0.272 watts per CFM. If you think you have about a 50-50 mix of ducted and surface mounted, then you can just describe it as mixed, and you'll get a value that's the average of the two above numbers. If you don't like any of these numbers and you want to enter it yourself, you can just enter watts per CFM the way you normally would, or however it's just you can, whatever method you want to use for handling the fan power in a PVVT system, you can use. But this is just a way to get a default that is kind of based on the type of system you're looking at in the zone. So the next item here is the VRF refrigerant piping. And there are three categories that are defined in the input for DOE 2.3. There's the leader category, which is defined as the length of pipe that goes from the outdoor unit to the first branch. So this first segment out here leading up to the first branch. And then there's the header, which is the length of pipe from the first branch to the last branch. And then there's the branch, which is the length of pipe from this header to any individual indoor unit. So each indoor unit has its own length of branch that can be defined. And the purpose, the function of the piping in the model is that it accounts for energy impacts, both of thermal loss through conduction through the pipe and radiation to the environment, and then friction loss of flow of the refrigerant through the pipes. So both of those are accounted for in the piping. And I'll talk a little more about that. And so, yeah, here's the piping inputs. So the leader and header pipes are defined at the condensing unit. So the condensing unit component in the model is where those are defined. The branch pipes are defined at the system. So each system can have its own characteristics for the branch pipes. And then each pipe has a group of keywords that relate to its performance. So there's the length of the pipe, and then there's also an equivalent length for pipe fittings. And the reason those have to be separated is the length of the pipe relates both to the conductive heat loss through the pipe wall and also to the friction in the pipe, whereas the fittings only relate to friction, so they have to be kind of handled separately in the model. Then there's the location for the calculation of the heat loss or heat gain, and it's specified either as outdoor or zone. And then if it's specified as zone, then you actually have to identify the name of the zone that that the piping is located in. And there's optional input of piping diameters for the low pressure and high pressure gas pipes, which is where most of the energy impacts are. And by default, those pipes will be calculated by DOE23 based on the system capacity and using kind of industry standard rules for sizing those. And that's probably the safest thing to do to make sure you don't get weird piping sizes that overestimate or underestimate your losses. The biggest risk is overestimating the losses due to pipes that are too small. For the header pipe only, there's a mechanism for kind of accounting for how the pipes are distributed along the header, how the branches are distributed. So if the branches are completely evenly distributed, then the value for this header adjustment is 50%. If the branches are all down at the far end of the line, then you would use 100% value for this adjustment. So that gives some flexibility in how the piping distribution works and how the losses are accounted for in that. Okay, so the next couple slides are related to sizing, and these sizing adjustments mainly relate to the piping losses. So this first one is for the indoor units. So this is at the system component or the indoor unit component, and there's a keyword called number of units. And basically the purpose of this is to account for abstraction in the model, where you might have a large thermal zone in your model that actually represents a bunch of zones in the real building. So I'm kind of demonstrating this with an example. Maybe this could be an office building, and you've got 9 zones in a strip that you have in a single thermal zone in your model. And in terms of the VRF units, you may know that you're going to have, for every 3 of those zones, you're going to have 1 VRF unit that provides conditioning to each of those. So you might have like a little ducted VRF indoor unit for each 3 zones. And I just got a pop up on my computer saying there might be some connection difficulty, so hopefully everyone can still hear me. If there's a problem, you can send me a chat, and I should see that.
Hey, Doug, can I ask a question here?
Sure.
Yeah, so this is Nick Caton with Schneider Electric. If we have a case of, say, a large perimeter, like open office area or something, and we anticipate the need for perimeter versus core zoning, do you know, in the case that you're doing this model specifically with VRF, is it preferable, would you say, to proceed with normally zoning it the way you might for a normal system and have, say, a 10-foot perimeter set of zones for each facade and a core zone, and then specify like 1 VRF as far as number per units per zone? Or do you think that, is it better to make that one big zone and then put something above 1 on number of units?
I think generally it makes more sense to keep it one big zone as long as there's not a reason for diversity of loads to separate them. And that's the whole purpose of this functionality, is to allow you to keep your model simpler overall, but still give you accurate piping energy calculations. So this basically just splits the piping into three segments, three parallel segments instead of one large pipe. And so it gives more accurate results for the piping.
Okay, thank you.
Yep. So the next slide here is another methodology for basically accomplishing the same thing. And if you may not know, you may have a lot of abstraction in your model and you don't want to have to sit down and calculate how many systems are in each of your abstract zones. So you can use this max cap per unit to automatically determine the number of systems in each zone. It also kind of creates a safety valve for if you kind of erroneously get a bad number in your input and end up with a way oversized system. This will correct that automatically. So there is a default value for max cap per unit that will automatically reset the number of individual units, and if it's different from what you've entered, and if it conflicts with taking the ratio of this total system capacity to the number of units in your model. So again, it prevents getting giant loads on relatively small pipes. It's kind of a safety feature for the model. There are defaults for max cap per unit. And those I mentioned earlier is this VRF terminal type that could be surface mounted, ducted, or mixed, and the max cap per unit defaults based on that. If this VRF terminal type is an optional keyword, if you don't use it, then the default for max cap per unit is 2.5 tons. And if the max cap per unit does have an effect on your model, you'll see a little statement in the SVA report saying that the number of branch loops was set to some number based on the max cap per unit. And I'll just mention that I think my very last slide indicates that this max cap per unit was overlooked in setting up the eQuest interface. So that's sort of a bug in the program right now in the eQuest. It will function if you enter it manually in the INP file. There's also a workaround that Bill Bishop has posted out on the eQuest user list. And I'll try to post a file following Bill's instructions to my website for people who want to be able to access that through eQuest. So that was the indoor unit. This is a similar concept for the outdoor unit. And basically it accounts for abstraction of the model of the outdoor or condensing unit level. And it allows there to be a single very large VRF system that would serve a large area of the building. But in order to get the piping sizing to be reasonable, you divide it into some number of systems so that conceptually it handles the abstraction of the model and breaks it down into smaller set. And I've kind of tried to explain basically the concept that you might want to do this because of being able to model the simultaneous heating and cooling benefits of a VRF system. You may want to have that system be more broadly attached in your model than it really would be. So you kind of have to play around with the abstraction and figure out what makes sense for you. But this is kind of an example. I won't kind of go through the finer details of it. But again, my last comment here is that putting this affects the pipe losses, and it's important to get the abstraction adjusted so that you get reasonable pipe losses in the model. And so there's the number of systems, and there's also a max cap per system. So this is, again, the same concept of setting a threshold and doing an automatic adjustment in the program if you exceed the threshold, so that you don't get excessively large systems in your model. And if you exceed it and it automatically resets the number of systems, it'll put a warning message in the section of warnings that are above the SVA report in the SIM file. So here's another concept that might be confused with the number of systems, but it's called number of units. And what this represents basically is the number of compressors that are in one system. So if you've got 4 systems in your abstracted model, each of those systems is likely to have multiple compressors. And so this allows you to specify that number of compressors in each system that's in the model. And for example, you might have a 18-ton VRF system made up of 3 6-ton units. So you would have num units equals 3. And the importance of this is it affects the part load performance in the model and staging of those compressors. And there is actually a keyword for condensing unit called unit control that allows you to control how they get staged. And the default is that they would run together when possible. So if you're in a higher load range, all of the compressors would be running together and modulating through their variable speed range. But if they get down to the minimum speed rating, then they start to stage, even though it's in the run together mode. So there is some staging that happens in low loads for run together. Run stage, on the other hand, is more of a strictly staged system approach, and each one will still have variable operation capacity, but they'll stage one and on and off one at a time as load goes up and down. So here is a little bit more of an explanation of the number of systems and number of units, because that is a confusing concept. So I've tried to identify here what that means, what those two terms mean. So number of systems is kind of that abstracted number of complete sort of independent VRF systems, and units per system is basically the number of compressors in each of these systems. The capacity that's listed in the PSH report is the total capacity of all systems in all units. So there's this little formula. This actually prints out as part of the PSH report to give you a guideline of what it all means. So capacity is the capacity per outdoor unit times the number of units per system times the number of systems. And there's a little sample calculation of showing that up above. So talk a little bit about control. For the indoor units, there is a airflow control, and basically it can be variable flow or constant flow, and it's using the standard functions that have all been in the program for a long time for PVVT systems. And here are the inputs that I kind of arrived at as I was using the program. And for a variable flow system, I set air temp control to variable vol temp, min flow ratio to the value kind of based on the terminal units, and then the thermostat type to reverse action. So it can actually allow the airflow to rise up in order to satisfy heating loads, since there's no baseboards or anything like that in the model. And then constant flow, when I set this up for my modeling, I think I just kept it the same, but set the min flow ratio to 1 to force it to be constant flow. For temperature control, there are newer VRF systems that have been come out in the last few years have had some more advanced control scenarios where they can do reset of the refrigerant temperatures based on the load in the worst case zone. So that's a way to save energy in the system. For the outdoor units, there's first control is in response to the temperature control of the indoor units. So those temperature control scenarios I just mentioned. And then the other angle on the control of the outdoor unit is the fan control based on for the outdoor coil, and that would be a variable speed control. That's standard for all the systems that I've seen. And there's two different control scenarios that can be applied. As far as I can tell from what I've learned about these systems, is float to limit is the most common, or that's the only thing I've really seen. So that's the default in the program. But basically, that first it will float the refrigerant temperatures to whatever the max and min set point is for discharge temperature and suction temperature, depending on when you're in cooling or heating. And then you would reduce the fan speed once you hit that set point to hold the set point as the outdoor temperature drifts. But there's another scenario that's built in where the fan speed is reduced throughout the load range in order to create kind of more of an optimized performance of fan energy and compressor energy. But I haven't seen any description anywhere in manufacturer's literature to indicate that that's currently done. But if they pick up that technology, then that would be a way to improve the performance of the systems in the model. So those were the main things that you might tend to need to deal with as you're working with VRF models. But I'm going to talk a little bit about performance curves and also just a little bit about defrost. Those are things that you most likely won't need to manipulate in your model, but it's probably helpful to understand where the default performance curves came from and where the rated values that are built around those curves came from. So that's what I'll be talking about. So first, I'm going to make a comparison. So I mentioned that Energy Plus uses the similar kind of component-based model approach to DOE 2.3. And in part of our review of Energy Plus, we looked at the performance curves that are released as the default curves with Energy Plus, or in their sample building. I guess it's not really defaults there, but the structure of the curves in Energy Plus is that they have 3 pairs of curves, and each pair is at a different operating speed. So they're able to handle the part load ratio by having multiple pairs of curves. And the curves are capacity as a function of refrigerant temperatures, and power as a function of refrigerant temperatures. So I think the X's in the graph down here represent the speeds that they have in their curve set. And DOE 2.3 has a little different approach, but so in DOE 2.3 there's 3 curves. There's no pairing to speeds. The speed part of it is handled in the last curve, which is the part load ratio curve, and then capacity and EIR are handled in the first 2 curves. And this is similar to what's done with chillers in DOE 2 and with refrigerant compressors in DOE 2. But we wanted to make sure that this approach was compatible with Energy Plus. So I took the Energy Plus curves and reprocessed the data from those curves into the format of the DOE 2 curves and compared the result, and this is what we get. So you can see that there's a little bit of places where they're a little bit off, but for the most part, they're pretty close. So my conclusion was that the two curve methods are compatible with each other. And if manufacturers develop data for one, it can be converted to be used in the other. So that was a good thing. So this is looking at a couple of different compressor curves and also comparing to a cycling compressor in a two-speed heat pump. So the cycling compressor and the two-speed heat pump is the dots. And then the red X's and the bright green line are the VRF. The X's are from the VRF curve that we were just looking at, or the Energy Plus VRF curve. And then the bright green is data that I found for a Danfoss compressor, a variable speed compressor that's a 13-ton unit. And this is EIR as a function of part load ratio, and it's for a certain value of the delta T, kind of a mid-range value. And one thing to point out is that the Energy Plus is based on a 13-ton compressor, or they say, I guess in the Energy Plus literature, they say 12-ton, but the Danfoss is actually a 13-ton, which seems high compared to the compressors that I've seen used in the manufacturer's literature, tend to be 6 to 10 tons. So for the DOE23 release, we chose this 6.6-ton compressor from Danfoss as the default. The Energy Plus curves are still included in the DOE23 library, so if a user wanted to change and use those other curves, it's a relatively straightforward thing to do just by referencing the other curves in the definition of the condensing unit.
Hey, Doug, I got another question on the curves here.
Yeah.
So you mentioned in the prior slide the interchangeability potential between energy and DOE23 curves and similar. And I suppose for those of us who are going to start regularly trying to use eQuest in support of our design or performance specification of VRF systems, can you identify or suggest any particular places on the internet to keep tabs for if and when some new curves should be published?
I don't really have any ideas about that. Energy Plus website, I guess, would be one place where they would probably come up, and I guess the manufacturers eventually, I think, will get onto this and develop these curves, but it takes a while for them to adapt to the new methods. So there is an ASHRAE committee that's working on developing performance data protocols for different kinds of equipment, and I think they're planning to look at VRF in the near future. So hopefully that will speed things along.
Awesome. Thanks.
So the next few slides are kind of describing the process of going from published data to the model inputs. And I'm just going to go through this sort of quickly. And again, these are things that you probably don't need to understand in depth, but I kind of want to just put it out there and kind of document. This will lead to the default values that are in the default settings for VRF systems. So there'll be a table at the end of this that's kind of dense, but the purpose of this is just to kind of show you where the default values came from. So basically, the starting point is the AHRI data and an understanding of what's going on in the AHRI tests. So I've put together this table of what's some of the parameters of the AHRI tests and how they vary with the size of the unit. So one significant thing is that the pipe length that's specified to be used in the test is quite a bit different for very large units and very small units. So that's an important thing, and you'll see that effect when you look at all of the AHRI data on a chart, which we'll look at in a minute. And then it's good to know that the outdoor fan is included in the EER calculation. And as I mentioned earlier, the indoor fan power is included in the EER calculation. And then there's these temperature set points for outdoor and indoor dry bulb and wet bulb. Then there's some information that's not specified in AHRI that you need to kind of have an idea of reasonable values for. So there's the outdoor fan, airflow and power, and indoor fan, airflow and power, and the refrigerant, saturated suction temperature and cooling and heating, and saturated discharge temperature and cooling and heating. So we ultimately need to know those numbers in order to define what the efficiency relates to in the model. So this is a graph of AHRI database data for a heat recovery VRF system. And then I've also got the ASHRAE 90.1 standard values limits on here. And you can see that there's this stepwise change that is, I think, significantly related to the length of the piping run for each of these ranges. It's not exactly corresponding to that, but I think it's a significant factor. And then I think there's also some other factors that I'll talk about in a minute. So this is a similar chart for small multi-split heat pump units. So these are more like small commercial / residential scale units. And there's much less of a trend in this case because there isn't that association with piping lengths that we have with the big units. So here's a little more discussion on the change of efficiency with capacity. And on the left, it's the big units. And I've got it now as EIR, so bigger number is less efficient. And you can just see a real strong trend on average that as you get bigger, the efficiency goes down. And I think a big part of it is the piping length specification. I think another important thing is just kind of a form factor, how much surface area there is for rejecting heat relative to the capacity of the unit. So surface to volume ratio will tend to decrease as the capacity and just the overall physical size of the unit increases. Similarly, as when you get to the largest units or mid to larger units, the manufacturers start grouping together smaller units. And so if they're positioned side by side, then there's an airflow resistance that comes in from the sides that's going to tend to decrease the efficiency. So I think that's probably also a factor that leads to this trend. You see a little bit of that in the small units, but I think those factors are just less intense for the small units. And you don't have that grouping of units side by side, so that's not a factor there at all. So this is that big table I mentioned a few minutes ago. So these are default values that are automatically come up in the program based on the size of the unit that you specify. There's a keyword called tip cap per system. So that means this identifies the capacity of a typical system. And its whole purpose is to basically do a lookup in this table for the rated temperatures corresponding to a given size unit. So your actual model capacity could be something different if you have a general knowledge that your capacity is going to be typically about like this. So it's a way to kind of control the defaults that you get separately from the actual sizing of the model, which I found useful in the work that I've done with the program. Basically, there's a process to get at these numbers by looking at the outdoor temperature and the indoor temperature and accounting for the dynamics of the coils and estimating what the refrigerant temperatures would be at design operating conditions for the different sizes of equipment. And my recommendation is, unless you have a good source from a manufacturer that really understands what this is all about, my recommendation is to use these defaults, but do specify this typical cap per system to get the defaults to be reasonable. I think the tip cap per system will default to the actual capacity of your per unit or capacity per system in your model. So you don't have to enter that, but it's maybe useful to have an understanding of what you're getting. Another kind of technical topic is defrost, and we were developing the VRF. We found we wanted to be able to compare VRF systems to conventional heat pumps, and we were getting some odd results in conventional heat pumps when we started looking at the defrost energy of a VRF compared to the defrost energy of a conventional heat pump. And when we looked deeply into it, we found that there were some errors in the conventional heat pump defrost algorithm that was being used in DOE 2.2. So we've corrected those errors and implemented that for conventional heat pumps and used the same algorithm on VRF systems. And basically that algorithm has to do with how frost accumulates on a coil and how frost is melted from a coil. And the VRF system uses that same kind of physics-oriented algorithm, but it has a different algorithm for how the configuration of defrost happens. So in many of the larger, newer large VRF systems, there's a configuration where the outdoor coil is split into two separate circuits, and the compressor can operate during defrost where it draws heat from one of the coils and rejects heat to the other coil. So it can redo the defrost fairly efficiently and quickly by splitting the coil one way and then reversing it and splitting it the other way and defrosting both sides of the coil one after the other. So that's the model that is implemented in the current DOE 2 for VRF, but the heat pumps have a different approach for the configuration itself. So this is a fairly detailed study I did a couple of years ago when we were developing the VRF algorithms to kind of do some testing of different parameters of the VRF definitions and compare those back to the impacts of the different parameters back to a conventional heat pump. So the first two rows in this table are analysis of a building. It's a large office building in a cold climate in California, which it's a mountainous climate. So it has a significant winter and significant summer. And it is a 3-ton, 2-speed, relatively high efficiency air source heat pump. And the base case has an economizer, so it actually has relatively lower cooling. But to make it more of a comparable system to a typical VRF system, which typically do not have economizers, we took out the economizer for this step 1.1. And so this is a conventional heat pump with no economizer, but everything else operating kind of as a typical high performance 2-speed heat pump. Then I looked at a VRF heat recovery system. And again, this is a large office building, so there's a capability to do simultaneous heating and cooling recovery through that system. And it's the baseline is a 20-ton unit, which would have an EER of 11.1. And then I started making changes one at a time, but accumulating those changes to get to a point where the model was relatively similar to the conventional heat pump, just to see how the heating and cooling and fan power would compare in the end. So the first step was to reduce the piping. So large office, I think the piping was somewhere in the neighborhood of 100 feet. I've reduced it to 25 feet total, which would be more equivalent to a split heat pump unit. And you can see there's a few percentage points difference on heating and 1 or 2% difference on cooling and a relatively small difference on heating or fan power. So not a huge impact to basically eliminate the piping in the VRF system, but it's a factor. The next thing was to reduce the size. So started out with a 20-ton unit, and I went down, I think, to a 6-ton unit, which is kind of the smallest commercially available, just to get it into a reasonably close size category to the air side heat pump. And again, there's that improvement in efficiency with going to a smaller size. So that's the reason for doing that, because it gets closer to that high efficiency, small air source heat pump. The next step was to increase the minimum part load ratio. So if you're running the unit at low part load ratio and cycling, the efficiency is relatively poor. So it actually, increasing the minimum part load ratio actually bumps up the efficiency and reduces the cooling and heating energy by quite a bit. The next step was to change the indoor unit to a 2-speed instead of variable speed. So the main effect there is increasing fan power, which has a corresponding change in heating and cooling because of the higher fan heat. The next step was to remove the dedicated outside air system, and that was so that there's a fan power associated with that goes away, and then we've only got the fan power of the individual zone units. The next step was to increase the indoor unit fan power from being a typical surface. I think I used a kind of a mixture of terminal units and ducted units in the base case, so it was to change it all to ducted units, which would be more typical of the conventional heat pump. So fan power goes up again. And then the final step of the progression is to remove reset controls, which then again reduce the fan power and caused heating and cooling to go up some. In the end, the VRF system has slightly higher heating, slightly lower cooling, and similar fan power to the high performance 2-speed heat pump. So that's kind of what you would expect once you take away all the bells and the whistles of the VRF system. Then it's going to perform basically like an airside heat pump. Okay, so that's the technical content. The last few slides are about the Wizard, or the eQuest, I guess, and the first one is about the Wizard. If you wanted to go into eQuest and just whip up a simple model that has a VRF, you can do that by creating just a DX system, changing the heating source to DX coils, and changing the system type to variable refrigerant flow, and you can make it either a heat pump or a heat recovery type system. And then if you go back to the navigator and complete the model, you'll have a VRF sample system. And also you notice that it will by default create a dedicated outside air system, but you can take that away if you want. If you have an existing model and you want to add a VRF system to it, you can just go through the component tree to create a condensing unit, and then you give it a name and it'll prompt you for the header pipe location. And then I think if you choose zone, it will ask you for the zone. And then you can open up the condensing unit properties screen to enter most of the things that we've been talking about. I haven't heard of anything that we've missed on condensing unit yet, so hopefully that is complete. And then you can go into individual systems and set them to be conditioned by condensing unit, and then choose the name of the condensing unit that that system is assigned to it. And you notice that over here on the right, it's blank, and some users have discovered that the max capacity per unit is a keyword that's missing in this interface. And Bill Bishop has added that to his version of the program by manipulating some of the behind-the-scenes eQuest files. And my plan is to post a fix to my website for this, because it's a fairly simple thing. You just switch out, I think, one file. And in the meantime, you can either follow Bill's instructions if you want to modify that keyword value, or you can actually manually edit the input file if you only have a few condensing units that you want to do manually. So if you are looking for a specific keyword in the interface, this is a kind of a map that shows the list of all the keywords that are related to condensing units and where the name that they're given in the interface. And as I mentioned in the previous webinars, there's a file that you can go into in the eQuest directory called bdldialogues.txt that you can search for these things and figure out from that where they are in the interface. So if you can't find them, you can search for the keyword name and find it that way. Similarly, if you're looking at the worksheets, you can do that. So I've noticed a couple of questions popping up. I think that's the end of the formal discussion. So I'm going to just stop the recording to do questions and answers, because I think that's best.